Okay, so today we're going to be looking at first order separable examples. Okay, so these questions here are contextual questions, and the trickiest part, they're like particular solutions for general equations, but it's the data that tricks a lot of people, understanding what you're given, what it really means. Okay, so we'll read each question carefully and then we'll answer each bit. Okay, so a radioactive isotope of plutonium decays exponentially such that the rate of decrease of the mass of the isotope at any given time is proportional to the mass remaining at that time. So if m denotes the mass of the isotope in grams, okay, remaining t years after decay began, the decay is governed by a differential equation of the form dn by dt equals negative km, where k is a positive constant. Okay, that is a lot of information given to us about something even I don't know about. Okay, I'm not fully aware about isotopes and decay and all that stuff. Okay, all I know is that that's the equation that I'm going to be using. Okay, so therefore, let's see if we can go to part A and answer it. So we're going to find the general solution of the differential equation expressing m as a function of t. So you can see my two variables aren't x and y like they were when we've done the sort of particular and general equations or solutions we've done the last few days. It's m and t is what I'm looking at. Okay, so I need to get all my m's to one side and all my t's to the other side. Okay, so let's start by doing that here. So let's rearrange this. So if I rearrange this, okay, it's going to look like, if I bring that m over, it's going to be 1 over m dm equals negative k, and I'll bring that dt round the other side. Okay, so that's me swap them out. Now we know we need to integrate these, so I'm going to put on my integration signs. So that's what I'm solving. Okay, I'm solving that there. Okay, I'm going to integrate both sides to try and see if I can get the general solution. Okay, so if we do that, okay, well, if I integrate 1 over m with respect to m, that's one of our standard integrals. Okay, we get log. So we get log of m. Okay, that's going to equal, well, if I integrate negative k is just a constant. Yeah, it's like a number. So therefore, if I integrate that, it's just going to be attached to a t. Okay, plus c. Okay, we've got negative kt plus c there. Okay, so I want to get the general equation, so therefore what I'm going to do is I want to get m on its own. I don't have any data at the minute, so I can work out my constant. So I'm going to try and work out how to get m. Therefore, how do you undo a log? Exponential. So we need to take exponentials on both sides. So exponentials on both sides. Therefore, I'm going to get, well, if I take the exponential of log, the exponential will cancel, so it's just going to be left with m there. That's going to be e to the power negative kt plus c. Okay, so all that goes up to a power for the exponential. Now, if we remember our indices rule, that means that we can split up our power like that. So we've got e to the negative kt multiplying e to the c. That's what that would have been. And remember, e to the c is a constant as well, isn't it? Yeah, it's just a number. C is a constant, therefore the exponential constant is also a number. It's a different number though. So let's call that a, for example. Therefore, we're going to get a multiplied by e to the negative kt. Okay, and that is my general equation. Okay, it's general because I've still got a constant a, and I've actually got a constant k in the term that I actually was given in my equation to start with. But that is, I don't have any data to put into that. Now let's go back to our question to see if that actually makes sense. Okay. So it says that a radioactive isotope of plutonium decays exponentially. Okay. Now that sort of does help me think that I've done this right, because I have got an exponential function, but because the power is negative, it's going to go downwards. Yeah, it's decaying, it's getting down. So that looks like I've modelled that correctly. Okay, I've got a solution that looks like that should work there. Okay, so that's part A. We've managed to do that. So nothing's really different with part A at the minute. Okay, that's a question that if I took all the text away and just gave you the equation, we would solve it exactly like that. Okay, let's move on to part B. Okay. So given that this isotope has a half-life of approximately 139 years, that is, any initial mass of the isotope, one half will disintegrate into 139 years, in 139 years. Show that starting with 120 grams of the isotope, the mass remaining after T years is given approximately by this answer here. M equals 120 e to the negative 0.005 t. Okay, that's what we are asked to show here. Okay, and then hence, once we've done that, find the mass remaining after 50 years. So now you can see the contextual part's kicked in now, isn't it? It's given us some data. It's asking us to find some information, some physical example about this. Okay, so remember what our equation looks like so far. Our equation looks like m equals a to the negative kt, like that there. Okay, and you can see my solution will model that sort of thing. I just need to get the data. Okay, so let's start off with what we know. Well, I know that the initial mass. Sorry, I've highlighted the wrong bit there actually. Give me a second. Let's try that again, sorry. That if we start with 120 grams, okay, that's the initial part, then that means that that was at the very start. Now, t is time, isn't it? Yeah, after years. Therefore, the first thing that I can write down is that at time equals 0, the mass was 120 grams. Okay, that's at the very start of this process. Okay, so I'm going to put that information into my equation and see if I can work out a constant from that. Okay, so if I put that into the equation, the mass becomes 120. That equals a e to the negative k. K is multiplying by t, but I know t is 0. So I've got that equation there. Okay, I've substituted my values into my solution that I got for part A. Okay, anything to the power 0 is 1. Yeah, so all this here becomes a 1. Therefore, I'm left with just A. So what that's showing me is that the value of A, that constant that we got in the first case, is actually 120. So,
Yes, hence find the mass.
show that up here. Okay, we need to show that we get this equation first. Okay, so A equals 120. Therefore, what I've worked out so far, if I go back to my equation and put that in, that I know that the mass is 120 e to the negative kt so far. Okay, that's what I've worked out. The A was 120, so I can put that data in. Next, okay, I still need to work out the value of k. Now, I'm hoping I'm going to get 0.005 out of this, because that's what I'm asked to show, but I need to work out how to do it. The only other information I've known about this question, so I don't have any other data regarding specifics, but if I read the question carefully, it talks about half-life. Okay, so that is any initial mass of the isotope, one half will disintegrate in 139 years. Okay, so if it's starting off at 120 grams, in 139 years' time, what would the
60.
It'd be 60 at half, doesn't it? That's what half-life means. Okay. So therefore, I've got some more data actually. Okay. So when t is actually 139, the mass gets halved down to 60. Okay. And I'm hoping that might help me get the other part to the equation that I'm trying to solve for the constant k. Alright, so let's put that data in. So mass will be 60 now. That'll equal 120 e to the negative k multiplied by t, which is now 139. Okay, so that's what I've got there. Now a better way to write that probably now would be 120 e to the negative 139k. Okay, so that's what I'm trying to say. When 60 equals that, what value of k makes that become 60? Okay, So let's do some rearranging. We'll bring the 120 over to the other side, okay? So 60 divided by 120, that gives me a half. Okay, so I'm going to end up with a half there, equals e to the negative 139k. Alright. Now I want to work out k. Yeah? K is actually up at a power at the minute. I would rather get it down. Therefore, what would I take on both sides?
Log.
Logs, yes. I want to get rid of the exponential. So I'm going to take the natural log on both sides. Therefore, what I get is the log of a half equals negative 139k. Okay, that way I've got rid of the exponential there. And if I do some more rearranging, what k will equal, it'll be the log of a half divided by negative 139. And in your calculator, if you do that, you'll get an answer that rounds to 0.005. Okay, so therefore, what I've shown is that my constant k has become 0.005. Therefore, my equation is 120 e to the negative k, which is 0.005 t. Okay, so I've shown that with that information, we've managed to satisfy the particular solution that we were given. Okay, any questions about that so far? Okay, we've still got one bit left to answer. The bit we've got left to answer is, hence find the mass remaining after 50 years. Well, I can do that now, because all I'm going to do is substitute t equals 50, so that's how many years, into this equation to see what I get. Okay, so if I do that, m will equal 120 e to the negative 0.005 multiplied by 50. Okay, you can actually tidy it up before you put this into your calculator. You get 120 e to the negative 0.25. If you do that, which gives you the answer, space, 93.456. And the question is 93.46 grams. So that's how much grams of that original isotope would have been there after 50 years. Okay, so that's our first example shown to you. That's the answer to everything that the question asked us to do. You can see that there's a lot of parts to it, especially data-wise. Okay, this isn't as easy as the questions we were looking at the other day, where it just comes up, there's an equation, given that x and y equals this, find the particular solution. We've got to use the information to get our data. Okay. Any questions on that one before we look at the next one? No, we're okay. Notice how, I don't know about you, I had no idea about isotopes whatsoever. That the isotope wasn't, the understanding of it didn't really kick in, was it? It was about just reading it carefully and thinking about what data was there. Alright, that's how you go about answering these types of questions. Let's have a look at question 2. Okay, so a metal plate that has been heated cools from 180 degrees Celsius to 150 degrees Celsius in 20 minutes when surrounded by air at a temperature of 60 degrees Celsius. Newton's law of cooling states that if T is the temperature of the plate in degrees Celsius, so capital T is the temperature, after T minutes, so lowercase t, of cooling, then T satisfies a differential equation of the form d capital T by d lowercase t equals negative k bracket t minus 60, okay? And again, where k is a constant. Alright? So that's our differential equation that works for the information we've been given, okay? That's the sort of physical differential equation that satisfies what we're doing here, okay? Cooling temperature. Part A, find the temperature of the plate at the end of 1 hour of cooling, correct the nearest 0.1 degrees Celsius. Okay, so our job is to calculate the temperature at the end of 1 full hour of cooling. Okay, so let's go about doing this here. Okay, so let's start off with our equation. Let's put it back up so we can see the equation. Okay, so I've got two variables, capital T and lowercase t. This is separable. I want to separate them out first, okay? So therefore, what that will become, it'll be 1 over t minus 60, if I bring that t minus 60 over, d capital T, equals negative k dt. Okay, so that's me starting to separate them off. And again, we can now integrate both sides here, so I can stick my integrators and signs on. Okay, let's look at what we can do for both sides. So if I integrate that side there, okay, it's going to become log t minus 60. And again, if we integrate negative k is just a constant, so it's negative k t plus the constant c. Okay. Now, we actually have some data that we can use now to find the value of c. If I go back up to my question, in the first line, a metal plate that has been heated cools from 180 degrees to 150 degrees Celsius in 20 minutes. That means at the very start of this process, so before any coolings took place, it was at 180 degrees Celsius. Okay? Therefore, that will be my initial data. Okay? So I know at time equals 0. Okay? Therefore, the temperature was 180 degrees Celsius. I'm going to use that information. So I'm going to substitute that into my equation. So that's going to be log of 180 minus 60 equals negative k multiplied by 0 plus constant c. And what that will tell us, well, k times 0 is 0, that vanishes, so c will be left with the log of 120. Okay, so c equals log 120 there. Okay. So what I can do is I can put that back into my formula up here. So let's go back to where I was. So back to the start. Log of t minus 60 equals negative kt. Oh, not plus c anymore. Sorry, I've worked out plus c. It's log 120. Are we okay with that so far, folks? Yeah? Right, okay. Let's see what we can do with this now. So let's see if we can work out how to get our equation in the form of t equals here. So if I take exponentials on both sides to undo the log, I'm going to be left with t minus 60 on this side here equals e to the negative kt plus log 120. Okay, so I take exponentials on both sides. Again, I can split up my exponential power. So I've got that there. Okay. Now that exponential and that log cancel, and that would just give me 120. So that would eventually become t minus 60 equals 120 I'd get here, e to the negative kt. Okay. So that's what my equation looks like so far. Get the 60 over the other side, so we'll add it on, so it's 120 e to the negative kt plus 60. Okay. So this question asked me to work out the temperature of the plate after 1 hour of cooling. I still can't quite do that yet. Because if I put in t as 60 minutes, I still don't have a value for this constant k yet. And that's an issue. I need to get the value of k so that I can then work out the temperature. So I still need to do that. So therefore, I'm going to need to find more information in my question. If I go back up to the top, the only other thing I know is that after 20 minutes of cooling, it dropped down to 150. So I can use that information to help me get it. Okay, so I do have some more information down here. So if I go at time 20, the temperature dropped down to 150, so there's more information. I can use this to try and get the value of k. So therefore, put that into my equation, 150 equals 120 e to the negative k, t is 20, plus 60. Okay. Take the plus 60 over, so that's going to give me 90 equals 120 e to the negative k times 20 there. Divide by 120, 90 divided by 120 gives me 3/4. Okay? Yeah. So divide 90 by 120, I get 3/4 there. And I've got e to the negative 20 lots of k. And again, we need to solve for k here. So again, I'm going to take logs on both sides now, okay, to get rid of that exponential. So log of 3/4 equals negative 20 lots of k. Therefore, what k equals will be log of 3/4 divided by negative 20. Okay. And what that gives us is 0.0143, which we can round to 0.014. Okay. So I actually now have my value of k. So my equation was t equals 120 e to the negative k, which is negative 0.014 t, plus 60. Okay, that's me actually found the particular solution to this question. Okay, it's not me finishing the final answer because I've still got to work out the temperature after an hour, but I now can do it because all I need to do is substitute 60 minutes into the t part, and that's got enough information. Okay, so t equals 60. That's going to be 120 e to the negative 0.014 times by 60 plus 60. Okay, and that would give us, typed into the calculator, 111.805, which is 111.8 degrees Celsius. The question asks us to round to the nearest 0.1 degree Celsius. Okay, so there's a lot of steps to that one. Okay, we had to find the general solution. We had to put in the initial data we were given to find the first constant. We then had to find the value of k, so we had to use the other information we had about after cooling for 20 minutes that went down to 150. And then we had to get all that in order to find the question that was asking us, can we find after 1 hour of cooling? So after 1 hour of cooling, it is at 111.8 degrees Celsius. Okay? Okay with that? Okay. There's one last part to this question, so part B. Oh. When will the temperature of the plate reach 100 degrees correct to the nearest minute? Okay, so we still need to work out when will it go down to 100 degrees. So if I start off with my equation again, so it was 120 e to the negative 0.014 t plus 60. I need to work out what value of t would give me the temperature of 100 degrees. Okay, so I'll put 100 degrees into my equation. Okay. If I take the 60 off the 100, that gives me 40. If I divide it by 120, that will give me a third. So we've got a third equals e to the negative 0.014 t. Again, we've seen this before, now we're going to take logs on both sides to get to the exponential. Log of a third will equal negative 0.0. Oh, no, that's not right. Let's try that again. Too many zeros. 14 t. Therefore, t will equal log of a third divided by negative 0.014. Okay. Oh, bit too much there. If you substitute that into your calculator, I'll type that into your calculator, sorry I should say, you get 78.472, which is 78 minutes rounded to the nearest minute. Okay, so part B wasn't as big there because we'd done a lot of the work in part A to get the information we were asked for. Okay, so again, you can see with these questions, they are big questions. They're worth big marks. There's a lot of processes to it. The key bit is reading the question, not so that you understand everything about what the question's talking about, but understanding enough so that you can work out what data's given to you and how you can use that to work out your constants. That's always a trick. And then once you've worked out your constants, you can then answer a physical question like find the temperature after an hour, find the temp, or what time would it be to get 100 degrees, like that sort of thing. Okay, they're the questions I'm going to need you to try today. Okay, folks.